Introduction. So today I'm going to be talking about three broad techniques that you can apply to build robust, unbiased models. But before we go too deep into this topic, I just want to do a fun exercise with all of you. So there's some awesome brain power here. So I want to train all of your brains to detect malaria. So here you have a bunch of training data. They are labeled. The images on the left are infected cells, and the images on the right are uninfected cells. So please take a moment, train your neural networks to find some pattern that sort of help you identify cells that are infected. So let's take a few seconds for you guys to just go through the images here. Okay, all good? All right, cool. So I'm going to run through some tests just to see how well you guys did. So first test, who here thinks this is an uninfected cell? Okay, a few of you. The rest of you, I'm guessing, are infected on the infected camp. Okay, and a few of you unsure. So it looks like the uninfected camp, you guys are right. The rest of you, you need to tune your models a bit before we go to the next test. Who here thinks this is an infected cell? Okay, that's pretty much all of you. That's amazing. So your accuracy has gone up now. So it's gone up to 100%. It's indeed infected. And last test, this is a bit tricky. Who here thinks this is infected? Okay, less of you. And the rest of you uninfected? Okay, turns out this is an infected cell. So those of you who said infected, you're right. So let's try to understand what we just did here. Who here can tell me why they thought a cell was infected? Can anyone volunteer? Yes? The ring around the dot bit. Right, so there's like a ring-like structure around like a pink, red. Anybody else pick up on anything else? Yeah? The edges are more irregular on infected cells. Okay, yeah, so it looks like the edges are a bit irregular there. That may be the case for like a lot of the cases, so that's right. Anything else? Color, like red, pink. Yeah, so looks like all of you have like picked up on that pattern, and that's great. And so if you guys don't take away anything else from this talk, you guys are now experts at detecting malaria. But before that, let's take a step back and try to understand the process that we just went through. And I'm going to draw parallels with how we build machine learning models. So we're going to start off of course, with historical data, and that's what we did. We had labeled data, and we were training our brains. In this case, now we'll be training machine learning models, and we'll go through a cross-validation step that's quite iterative. And this is what we're going to do to tune our models, and we're going to evaluate the models on the val set. And if all is good, we're going to use that learned model to test on a blind set of data that the model hasn't seen before. And we're going to evaluate this using metrics like accuracy, and there are like a whole ton of other metrics that you could use. And if the model performance is acceptable to the stakeholders, then you would go ahead and deploy the model into a production system where now the model is exposed to new data that it hasn't seen before. And here, this is when things start to go wrong. This is where you might see that the performance is not as good as when you tested it on historical data. And there are two main reasons for this. One is the distribution of the data may be different now, so there might be some change in the behavior of the users of the system, or something may have happened where the distribution has changed, so this is data drift. And the other is maybe the historical data isn't representative of the population, so that could be some kind of a sampling bias. This sort of like reveals an oversight of the data scientist who was building the model. And the other main reason is data leakage. So this is where there's some information about the target variable that sort of leaked while you were training. And there was like a classic example of this in KDD 2008, where the competition was to detect if a cancerous cell was benign or malignant. And the winning team that got an accuracy of close to 100%, if I'm not wrong, basically used a feature which was the patient ID. And it turns out that that contained some encoding of how severe the condition was for the patient. And that sort of like tricked the team into thinking they built something wonderful. And so like all of this can be circumvented if we add this model understanding step here. And the main reason for doing this is to not just look at the data more closely, but also look at what the model has learned. And that's essentially the focus of today's talk. There's also another reason for doing this now with the GDPR, right to explanation. You sort of need to like answer this question of why the model came up with a prediction. And so this is a very hot topic. There are models that are inherently, transparent. And a classic example of this is a decision tree. And this is, a data set that most of you may have seen. It's essentially you're using 4 features of an iris flower to detect one of 3 types. You're trying to classify this into one of 3 types. So you have, 4 features here: the petal length, petal width, sepal length, and sepal width. And I use the scikit-learn open data set here to train a decision tree. And you can very easily visualize this as follows. And like what you see here is it's essentially a bunch of if-else conditions where you're finding splits in the data that minimize, say, entropy or maximize accuracy. And you can see that as you start from the top, the root node of the tree, the condition is if the petal length is less than 2.5, then you go to the left branch of the tree, otherwise you go through the right branch, and so on. And this is like really easy for us to follow. And this is essentially how we also think about problems. If you look at a slightly more complex data set, this is looking at the breast cancer data set. There are 30 different features here. And if we train a decision tree now, you get something that's a bit more complex. And this is essentially the complexity of the tree increases as the number of features increase. And you can, of course, like simplify this by setting a limit to the depth and also pruning the tree in other ways. But this is still understandable. You can very easily understand what this model is saying. There are, of course, other transparent models that you can use that sort of fall on the interpretable side of the spectrum. But what we're going to be focusing on are models that are slightly more complex, that have high predictive power, but not so interpretable. And let's see what kind of techniques we can apply there. So first step, let's look at the data and features. And one of the main things that we do is to look at the feature importance. And I'm going to make a case for going beyond that so that you get a much deeper understanding of models. So for feature importance, let's look at a concrete example. So this is a data set that I obtained from Kaggle, and it is a data set of high school students in the US. And the task is to predict their grade in math, reading, and writing. And the features that you have are these 5 features, which are gender, race, the level of education for the parents, the type of lunch that the student eats, and the level of preparation for the test. And as you'd imagine, when I built the model, the first step is, of course, to encode these features. And then I've trained a random forest model to predict the grade, which could be one of 4 types. That's A, B, C, or F. Now, once you've trained the model, the accuracy was pretty decent. The next step is to look at the feature importance. And that's one of the first steps that you would do. And so looking at the feature importance here, across the board, for math, reading, and writing, it looks like the 2 most important features are the parent level of education and race or ethnicity. And this is an interesting insight, but it doesn't give us the whole picture. Like what feature importance tells us is, like, on a global scale, what's the average impact of each of these features in predicting the outcome. And it does look like it gives us some sort of information on what the 2 most important features are, but it doesn't tell us how different levels of education impact the outcome, and also how these 2 features interact with each other. And this is where you can start to look at partial dependency plots. And I'll zoom into the one on the left here, just so that you can see what's going on there. So the first is, let's look at the most important feature, which is the parent level of education. Now, if we want to see how different levels of education impact the outcome, what partial dependency plots does is it looks at these different values for the parent level of education and assumes that you know all of the other features and looks at the average impact of each of these different values. Now, on the x-axis, the level of education basically increases as you go from left to right. So it starts with high school, goes all the way to the bachelor's degree, and then master's degree. And you can see that in general, as the level of education increases, the impact on predicting grade A increases. And this sort of makes sense. And the model seems to have learned this pattern quite well. But what if we want to look at how the parent level of education, how that interacts with race or ethnicity? So this is where you can now look at the feature interaction plot. I'm looking at 2 different features here. On the y-axis is the parent level of education. So as you go from bottom to top, the level increases. And on the x-axis are 5 different groups that you have. So, and also the other thing, I'm not sure if you can see the color, but a darker shade or blue means low impact, and a lighter shade, which is green or yellow, means higher impact. So if we zoom into one of these groups here, you can see that as the level of education increases, the impact on predicting grade A sort of increases. The color sort of moves from a darker shade, which is violet, all the way to like green. And you would expect to see this. Like you shouldn't, there shouldn't be, unless these two features are highly correlated, you would expect that regardless of the race, it should only be dependent on the level of education and the preparation for the test and so on. But what's going on with group 4 here? You can see that a parent with a high school degree has just as much impact as a parent with a bachelor's degree. And this sort of exposes 4 different problems. There could be like 4 different problems here. One is that partial dependence plots don't work very well when the features are highly correlated. So you may need to go back and look at whether these two features are indeed correlated. The other is there might be some kind of sampling bias here where group 4 isn't properly represented, or the model hasn't learned any pattern here. Or the fourth problem is that there's some systemic problem which becomes much harder to solve. But it turns out that in this data set, group 4 wasn't properly represented, and that's why you're seeing some weird impacts here. But the main point is that none of these insights would have been possible if we had just looked at the feature importance. So it's important to like go a bit deeper and make sure that the model has learned all of these different patterns so things don't go horribly wrong when you deploy. To implement this in Python, I use the PDP box library. This I found to be much better than the scikit-learn implementation, because as you would expect, PDP should be agnostic of the model, whereas the scikit-learn implementation expects you to use a gradient-boosted regressor or a gradient-boosted tree implementation, whereas here you could feed it any model. And the first line here shows you for a given feature how different values impact the outcome, and for the second one, you can feed it a list of features to look at feature interactions. And by the way, all of this code is in the repo up there. I'll share the slides later on or after this talk, so you can have a look at the code. Now, the next technique I'm going to talk about is post-hoc explanation. So let's go back to the breast cancer data set. So say that you've trained this deep neural network, or maybe random forest or a gradient boosted tree, and you learn this complex function that separates the benign class from the malignant class. And this is like really hard to explain because it's a nonlinear function. You have no idea what it's doing. So one way to simplify this is to pick one instance that you want to explain. So here, let's look at, say, one malignant case that you want to explain. Let's perturb the features to look at cases around it, assuming that they share similar properties, and you fit a linear model around it that's sort of faithful to all of the data points around that instance that you want to explain. And because you're training a linear model, it's much easier to explain because it's a transparent model. You can just look at the weights of the explanation parameters, and that sort of gives you an indication of how do cases that are similar to that behave. And this is basically the theory behind LIME, which stands for Local Interpretable Model Agnostic Explanations. And this is another view of it. So you have data that you learn a complex function, then you pick an instance x prime, and you train a linear model G that sort of approximates the complex function f around that point x prime. And the parameters of this model are sort of the explanation parameters, and that's shown here. We're going to be looking at an improvement to LIME called SHAP. The implementation is better as well, and the explanations that you get seem a lot better than the LIME explanations. So going back to the breast cancer data set, you have 30 features here. I've trained a random forest model that predicts whether it's malignant or benign. I'll show the code later on. The accuracy is pretty good. And then I use the tree explainer class from the SHAP library to explain one instance like this. So again, I'll show the code just so that this becomes clear. So switching to my notebook. So this is the repository up on GitHub. I'm running the SHAP-Tree Ensembles notebook locally right now. So here you can see that first I'm loading the breast cancer data set from scikit-learn. These are all of the features, splitting it into train and test, and using cross-validation to pick the best hyperparameters here. And looking at the best model evaluating on the test set, you get an average precision of 100%, which is awesome. And then the next step is once you've installed the SHAP library here, which is easy to install using pip, you then initialize the tree explainer class, initialize it with the model that you've trained, and you generate SHAP values for all of the instances in your test set. Okay. Now here, what I'm doing is this line of code is basically explaining the first instance in the test set. Sorry, this is the first instance in the test set, and it turns out to be a malignant case. And what you can see is that the base rate is roughly at 62%, and you can see how each of these feature values push the base prediction up to 90%, which was the final accuracy for that case. And what you can see is that the red the red color here means that it has a positive impact, and blue means it has a negative impact. And the larger the width, that means more the impact. So features like the worst concave points and mean concave points, these values sort of push this all the way up to 90% at the end. And what this is good for is you can very easily deploy this, or before you deploy it, you can test this using an actual expert. So if you have a human in the loop, you can show each of these examples and look at how the model arrived at the final outcome here. Looking at a benign case, again here I'm just looking at the probability that it's a malignant cell, and here it's basically 0%, so the probability of being benign is 100. And you can see how each of these values pushes the base rate down to 0 at the end. You can also look at a summary plot which shows the average impact over all of the cases in the test set. And again, the two most important features here are the worst concave points and mean concave points. And you can also look at feature interactions similar to the PDP plots that I showed earlier. So what this shows is different values for the worst concave points plotted against different values for the mean concave points. Red means positive impact, blue means negative impact. Now you can see that higher values for worst concave points and higher values for mean concave points have much stronger impact in predicting that the case is malignant, whereas lower values have lower impact in predicting that it's malignant. So these are just like another tool that you can use to like get a much deeper understanding of what the model has learned. You can of course use SHAP to look at deep learning models. So here I'm using the MNIST data set, trained a convolutional neural network, and then use the SHAP deep explainer class to come up with an explanation like this. So here I'm basically looking at a superpixel. So converted the raw pixels into a superpixel and looking at the impacts just to simplify the problem for the deep explainer. Look at what impact a superpixel has on predicting each of these digits. And let's zoom into one case here. So if you look at digit 0, what this shows is that pixels that sort of form the digit 0 have a strong impact in predicting that. And also the lack of ink in the middle also has a strong impact in predicting digit 0. Similarly for 4, the lack of a connection between the top two lines is sort of why this makes it a 4 and not a 9. And this is basically an explanation for this, just looking at cases that are around it. And this is interesting. But this doesn't work well all of the time because the decision boundary may not be as good as these two cases here. This was like a cherry-picked example, but like for cases, at least this like gives you a bit more insight into what the model is learning by just looking at cases around it. Okay, so the last technique, I want to talk about how you can mitigate bias if it does exist. So if the model has somehow implicitly learned, say, subtle biases in the data, how do you deal with that? And the picture here is of this researcher, Joy Bolamwini, who basically started this algorithmic justice league, and she's like out to fight bias in algorithms. I would highly recommend listening to her TED talk, where she found biases in like face detection algorithms, where like these algorithms were much better at detecting white faces than black faces. And so this was like a serious problem that was exposed, and so that you don't have to deal with it when you're building your models, let's like look at techniques that you can use to mitigate it. So one technique that I've been recently looking at is adversarial debiasing. So this was a paper that came out of Stanford and Google. The main idea here is you're basically training an adversarial network here. The first network is the predictor network that predicts the target variable. The second network is an adversary that tries to predict a protected variable. And what this protected variable means is basically a variable that is a proxy for a feature that you're trying to unbias. So if you want a model that isn't biased towards a given race or a given gender, then you would use the protected variable to somehow capture that feature. And what the predictor is trying to do is you're going to update the weights of the predictor in such a way that you throw the adversary off in being able to predict that variable, that protected variable. So the idea here is the adversary shouldn't be better than, say, randomly picking a gender. So that's basically what the predictor is trying to do. So this is sort of the theory behind adversarial training, and that's essentially what this architecture is trying to do. And we're going to be focusing on one of these, the definitions of fairness, where basically the prediction is independent of the predicted variable. So let's look at a concrete example just to make this clear. So if we look at the word embedding analogy task, so embeddings are a powerful mechanism for projecting discrete words into a real subspace. So basically the dimension of the real subspace would be much less than the number of words in your corpus. And one algorithm that you can look at is the skipgram algorithm, which basically looks at context of words around it to predict the given word. And unfortunately, like using the corpus that you use, or depending on the corpus that you use, it could, so if you look at this analogy task, which is he is to she as doctor is to what, you start to see cases like where woman, mother, pregnant sort of like show up in the top set of words here. And this is clearly showing some kind of like implicit bias in the corpus that the model has picked up on. So how do you deal with this? Clearly the task here is to find a profession that sort of is gender neutral here, or you want to like find a gender neutral answer here. So I've been trying to reproduce this paper using this notebook here, adversarial debiasing. This can be found on my GitHub repo if you go to the adversarial debiasing branch. This is still a work in progress, but if anybody wants to help out, please feel free. This is the link to the paper, and this notebook is based on another notebook that implements the same algorithm, but I've made some minor tweaks and made it compatible with Python 3. So the first step is, of course, installing GenSim so that you can easily load Word2Vec embeddings. And I'm basically loading the Google News Word2Vec file here. And the first lines of code, basically looking at this analogy task and seeing what answers come up using the current embeddings that were learned. And this is the output that I showed earlier. Now, the next step is to define the protected variable of embedding. So we need some representation of gender. So what you can do is you can look at pairs of words that clearly the difference between them is clearly just the gender. So if you look at woman, man, her, his, she, he, and so on, these clearly, the difference between them would sort of like the strong feature here is the gender. So just looked at the difference between these pairs of words, applied PCA to like come up with a vector that represents the gender direction, and that's shown here. And essentially what the adversary is trying to do is trying to like maximize the projection of all of these words onto this gender direction so that its task is basically to predict the gender. And what the predictor is trying to do is trying to throw off the adversary so that it gets really bad at that task. And that's essentially the adversarial model training section here. The main thing to note is that when you're training an adversarial network, it's quite tricky. It's quite sensitive to the learning rates. So I've picked a very low learning rate here. Of course, you can play around with this to see what results you get. But these were the hyperparameters that I used. And after training, if we look at this analogy task now, you start to see words that sort of define the profession rather than just random words that are sort of similar in context. So you start to see gynecologist, physician, pediatrician, and so on that come up as with a much higher score. And of course, like one thing that I'm struggling with is to know when you're done, when you know that you've sort of like removed all of the possible bias, and that I realize is not possible. It's just you can just like mitigate as much of this as possible. So the way that I was thinking of doing was getting some kind of human in the loop to like understand or gauge how well this new model has learned this analogy task. And so that's the last technique. And of course, this isn't everything. So just to summarize here, so we want to include model understanding into our data science process so that we can gain a much deeper understanding and not deal with these embarrassing situations of poor model performance or biases that the models are exposing. Be mindful of your audience. Like interpretability means different things to different people. For like us, or like majority of us, it sort of is to build better models. But again, if it's a business stakeholder, it's so that they gain more confidence in what the model is doing, so you can hand over more tasks to it. You can, of course, apply these interpretability techniques to, again, there's no silver bullet here. You need to look at it from different angles to gain a much deeper understanding. So apply these tools and it'll like help you with your modeling process. And finally, use the adversarial debiasing technique if you can to mitigate bias. Again, here we've only looked at the supervised learning problem. For unsupervised learning or any other type of scenario, that's still an active area of research and there's not much. But again, this is a good start for us. And in terms of additional resources, I've written a blog post on this which sort of covers what I just talked about. All of the source code is in that GitHub repo. There are, of course, other techniques that you can use, and there are links to this that I've provided here, 2 pages of this. The book, the last bullet point here is also great. There's, of course, the counterfactual explanation. So I wish I had more time to go through all of this, but again, these are links for you to get more information. And with that, that's the end of the talk. I'm going to open it up to a few questions if you have any. Thanks.
Any questions?
There are 2 here.
I believe there was a follow-up study after the paper set pointed out the bias of he is to she as doctor is to question mark, in that the algorithm they used to pick the relation excluded the same thing, so it would not pick doctor. So it's actually introducing its own bias in the bias detection in a sense.
Sure, yeah.
So is that something that you sort of accounted for in your work?
No, I mean, so that's, yeah, the thing is, I haven't in this example here, but then like one thing that you may have noticed is that nurse still turns up as the top word, even if like how much ever you try to like, if you want to believe that shouldn't be the top word, but it turns out that the context always contains doctor and nurse in the same context, so you can't, circumvent that problem just because doctor and nurse sort of appear together. So it's not showing the gender stereotype, it's just showing that doctor and nurse are sort of very similar in context, or they appear together. So there has to be a better way of learning these embeddings rather than just looking at the context or semantic similarity here. But yeah, that's an interesting problem. I haven't looked into it. Yeah, there's one.
Awesome talk. I wasn't aware about the debiasing, so thanks for sharing that. But I was of line and chat. Small question.
Yep.
Does that mean, I feel like the talks always talk about line and then immediately chat.
Yep.
Is anyone using line anymore? Is it worth digging in, or just
No.
go straight to chat?
No, I mean, you can still use line. I mean, it's sort of essentially like all of these different techniques are like additive explanations. So they use the same framework. It's just how you come up with the explanation parameters. That's what is different. Like SHAP uses Shapley values, whereas Lime uses simple linear model. So there's not to say that one technique is better than the other, but it's just from a visualization standpoint, I sort of felt SHAP gave much better visualizations than the Lime implementation. And so that's what I've gone with. And the SHAP paper sort of gives a framework that sort of covers Lime, other techniques like deep lift, and so on. And so you can use any of those techniques as part of the SHAP library that I'm using. So it's not just that I preferred SHAP because it's a better algorithm, it's just because it encapsulates all of them. Yeah. One question there.
Hi, thanks for a really good talk. I have one question, a small comment on the first question just now. It depends a bit on who you're trying to convince. I've had it that people are familiar with linear algorithms,
Yeah.
linear methods, and then they like Lime.
Okay.
If for a complete novice, maybe SHAP's better. I had a question with the adversarial debiasing, which I thought was really cool. For a stopping thing, have you looked at maybe just flipping it? So how is the answer, or like sub-narrative, the answer if you say she and doctor is the same to he and...
Yeah, that's a very good question. I haven't tried that. I want to after this talk, but yeah, that is a good question. Yep.
Yeah, thanks very much. It's a very important topic. Have you looked at any of the sort of powerful interpretable models like GA2M or SLIM or any of those? You got anything to say about those?
So I know that there are like people who prefer GAMS mainly because it gives a high predictive power. At the same time, it's interpretable. I haven't like personally used them, but of course there are like a lot of libraries out there that have come out from various people that implement GAM as well as GA2M, which is an implementation of GAMS that look at interactions between features and not just look at functions of one feature alone. So there are these different implementations that you can look at. I think GA2M was shown to be a lot more powerful than GAMS, but yeah, I wish I could talk more about it, but yeah, that's certainly one technique that you can use.